With this proposition in hand, we are ready to give the explicit formula for the conditional exploitation of x given f when f is finite. But before that, let us look at the very special case when f is generated by just one non-trivial variable subset. We'll write this as proposition number 2. Again, let omega a p be our probability space, and take a variable subset a in script a. Let x be a real random variable. Then the expectation of x given the subsequent algebra generated by this single set A. Again, like we did before, I'll leave this for you to think about, and then I will give you the answer through the proof. So let's start the proof. And you will see what this guy is at the end. Know that by proposition number 1, we know this guy is something really simple. Because this sigma algebra is generated by just one variable subset A. If you recall the statement of proposition number 1, so if omega is the disjoint union of f1 through fn, and then any variable function y will have this form. In our situation, this omega is written as the disjoint union of A and A complement. So from this disjoint union, we obtain this guy, which by the definition of conditional exploitation, this part is sigma A variable. So by proposition number 1, we have that this guy must be some constant a1 times the integrator function over a plus a2 times the integrator function over a complement. Now, we would like to find what a1 and a2 are. The way to find a1 and a2 is by taking integrals and use some properties of conditional exploitation. Specifically, we're going to take the integral over the domain A. And this will kill this part. So taking this integral yields for the left hand side we get, and for the right hand side, the right hand side is really simple, because if two sets have empty intersection, the product of their integer functions must be 0. So this part will become 0. So product here will become just a1 times the indicator function over a. But you know this is nothing but a1 times the probability of a. So right hand side is simple. Now how about the left hand side? Here we're going to use some properties of conditional expectations. First, because the indicator function over a is sigma a measurable, so we can put this function inside this conditional expectation. So this is because this guy is
the law of total
sigma
expectation.
Measurable. Now, the expectation of the conditional expectation is just equal to the expectation of the random variable inside. So this guy will give you just
the law of total expectation.
X times the indicator function over a. This is by so if the probability of a is non-zero, then a1 is equal to this guy divided by P of A. And you know by the definition of expectations, which are really integrals, the meaning of this is that this is really the average value of x over the set A. Now we find the coefficient a1. How about a2? Similarly, we can find if P of a complement is non-zero, then a2 will be equal to this guy with a replaced by a complement. So this gives the explicit formula for this conditional expectation when the sigma algebra is just sigma of a. So let me copy it down here. Under the hypothesis, if the probability of a is not equal to 0 or 1, now how about the trivial case when P of a is equal to 0 or 1? I will leave a remark below. So what happens when P of a is equal to 0 or 1? In this case, we have this conditional expectation is just equal to the expectation of x. Because in this situation, sigma of A only consists of sets with trivial probability, namely the probability of 0 or 1. And from probability theory, you know, in that case, x will be independent of the sigma algebra sigma of A, which we can check immediately. So this is because x is independent of sigma of A. When P of A is 0 or 1. And this equation follows from one of the important properties for conditional expectations. If x is independent of the sigma algebra, then this conditional expectation will become just the expectation.